Okay, let us start. Okay, so Alhamdulillah. So we will continue with the exciter and automatic voltage regulator models. We have developed models for synchronous generator. We have second, third, fourth, seventh order model for the synchronous generator only. Now we will start discussing the models for the excitation system. So this will be added to synchronous generator and also mechanical part of the governor and turbine. So we will add these models to synchronous generator in order to have the complete model of the plant. As far as we are interested in dynamic stability, few seconds after the fault, then in our model, we will not consider the mechanical part. We will assume that the mechanical power is kept constant during these 2-3 seconds after the fault. So this is the excitation system, general model of the excitation system. You have here some filter or measuring device, and usually we take TR equal to 0. So terminal voltage, V reference, and the error, if we have the error between the terminal voltage V reference and the automatic voltage regulator, will keep Vt equal to V reference through the adjustment of the field voltage and the field current. This is the excitation, so we have flux, and we may have some saturation, and this is the saturation factor. And since the exciter could destabilize the system, then the Ke is negative. In this case, we have what we call the destabilizing transformer. We discussed all these blocks in details, block 1, block 2, automatic voltage regulator, and then the limiters, the fourth block, which is the exciter. And we have here the saturation factor and also the stabilizing transformer. And we covered all this. Neglecting the rectifier, okay, and then we can, as we mentioned, if we have this block diagram, if we neglect this block, so we have here 3 integrators. This is the first one, second one, and third one. After each integrator, we can have a signal here, VF, and here is VR. So this is VR, and this one is EF3. With this block diagram, you can develop this model. So it is quite easy. For example, the signal here is, you can have it here, VR minus SE. So the signal here is VR minus SE. So this signal will be multiplied by 1, and EFD will be multiplied by KE-STE. So you can write KE-STE, KE-EFD plus STE-EFD KEFD plus STE-KFD EFD equal to VR minus SE. So this is EFD dot equal to 1 over TE will come here, and then this TE will be, you have here VR minus SE minus KE-EFD. We have here this is This is, by the way, it's not SE, it is SE if D. Are you following يا شباب? The signal here is EFD multiplied by this factor. So this is SE EFD. It's not SE, it is SE EFD. So you have here is SE EFD also. And this is SE EFD. Is it clear? Ahmed? Sulaiman? Yes.
Yes, SE is equal to EFD, right?
SE function, a function. A function of EFD. This function could be, and SE is not constant. SE is a scalar value, but not constant. It depends on the excitation system, the excitation level. يعني maybe if EFD مثلا, for example, if EFD equal to 2 مثلا per unit, then SE will be مثلا 0.5. If EFD equal to 3 per unit, SE may be equal to 0.7. If EFD equal to 1, then SE equal to 0.1 مثلا, for example. So it is a scalar value, depends on the EFD, function of EFD, right? So this is the factor will be multiplied by EFD. This is SE, scalar value, and will be multiplied by EFD here, so SEFD. So this is the first equation, and definitely you can have the second equation and third equation. So with this block diagram, with this excitation system, is it clear, Ahmed?
Yes, Doctor, yes, clear.
With this excitation system, we have a third order model for the excitation system. So if we have this system with the third order model of the synchronous generator, so the synchronous generator and the excitation, now we have sixth order model for SG plus exciter. Okay, so we can add this. Of course, if you still remember, the third equation there in the synchronous generator model, it has EFD. It has EFD in the third equation. I don't know if you still remember this or not. Do you still remember the equations of the third order model? It's not here. It's not here, but
yes, doctor.
Definitely you can write EQ prime dot. EQ prime dot equal to 1 over TDO prime multiplied by EFD minus KA multiplied by VT, V reference minus VT. Am I write it correctly? Is it okay or do I? Okay, let me.
It's different, Doctor, than the last one.
How much? What is the EFD prime equation? Can you tell me what is the EFD prime equation? EQ prime dot?
EFD prime or EQ?
EQ prime dot equal to what?
1 over T prime.
We have here swing equation. Okay, so we have the second order here. And EQ prime dot equal to what?
1 over T prime D.
Okay.
Multiplied by EFD minus EQ prime minus parentheses xt minus xt prime multiplied by id.
ID.
Yes.
Okay, so this is EQ prime dot, and this is EFD dot. You have it here, and EFD depends on VR, and VR dot depends on VF, and VF dot is given as here. So of course, EFD dot can be replaced. You can replace it here by this value. So you can have the third order model of the excitation system. So in this case, you have third order model of synchronous generator and the third order model of exciter. So our system now has 6 states. Of course, you can, in real life, you have a very complicated, type of stabilizers. It is not only as you can see here, very simple, but let us approximate this later on. So excitation, saturation now. What is SE? What is this factor? How can we calculate this factor? So of course we can approximate this saturation as exponential function. This is a very typical, excitation or no load characteristic of the synchronous machine. You have here the field current, IF, if you still remember this from even the undergraduate. So, and this is the E. So you can have E versus F as saturation curve. You can approximate it as the air gap line, straightforward, air gap as linear characteristic. If you include the saturation, then you have this BH characteristic as or BH curve as very well known. Now, if this is the air gap, air gap means no saturation. The air gap is no saturation. So this is B with no saturation. If you get the E for a certain, field current, if you get it from the BH curve with saturation, this A gives you the field current with saturation. This is without saturation. So the saturation factor is measured by or is proportional to the distance A minus B. So can we calculate this SE? Can we approximate the saturation characteristic of the synchronous machine or the excitation system to get SE here? Yes, this is some standard equation. We can no load air gap and constant resistance, and if the excitation of the air gap, excitation of the iron equals this, the saturation SC is defined as a function of EFD, and this is defined as the difference between with saturation minus without saturation over this. So SC is defined as such, and you can approximate the saturation can be approximated by exponential model, and you can express it as exponential. It is a function of SE, a function of EFD. So you can approximate this function as exponential, and you can have two values in order to get the complete equation. So this is as recommended. You can express SE as a function of EFD as exponential function. So you have here a constant e to the power another constant BE times BEFD. In order to get A and B, these constants, so you can have two measurements for the saturation at a certain value of EFD. So if you know SE at a corresponding EFD, then you can have one equation in A and B. And if you have another measurement of SE at a certain value of EFD, so you can have another equation. So you have مثلا S1 equal to A e to the P times EFD1. So if this is known and this is known, so you have one equation in A and B. And also S2 equal to A e to the power P EFD2. So if you have this one and this one, you have another equation. So if you have two measurements, you can get the A and the B constant. If you divide, and then you can get the len of both, so you can get B, and if you substitute in any equation, you can get A. So this is the way to get this saturation factor here. It is, of course, due to the, or according to the standard, they have two measurements, one at 0.75 EFD and the other at full load EFD. So you have two measurements, one at full load and one at 0.75 of full load. So if you have these two measurements, you can get A and B. This is the first one, this is the first measurement, and this is the second measurement of 0.75 EFD. So you can calculate this, and then you can, with these two equations, you can get A and B. So of course you can get A as such, SE over SE max to this power, and BE if you get the len, so you can get this equation. So if you have A and B, you can express now SE at any value of EFD. You can have the value of SE. So if you have any value of EFD, you can calculate now how much the SE corresponding to this excitation level. You know now A and B. So this is the saturation curve. So do you have any question, Abdulaziz, Johnny?
Yes, Doctor. Here, when we talk about saturation, are we talking about the AVR itself or the generator stator?
Again, your question?
My understanding is the DC exciter is connected to the stator of the generator, right?
Yes.
So is this the saturation of the stator?
Wait. You mentioned the exciter is connected to the stator?
Stator, yeah.
لا, الستاتور فيه 3 phase winding. The stator of the generator, you have 3 phase winding. You have here, assume it to know the salient pool just for explanation. So here you have the field winding, right? You can see the magnetic circuit now. The magnetic circuit, the flux is going from here, cross the air gap, go through the yoke here, and cut this and back to this. So this is the magnetic path of the flux. Okay, this is the north, this is the south. So this is the magnetic path. So we have here iron core. You have iron in stator, we have iron in rotor, and in between we have an air gap, right?
Yes.
Is it clear about this? Saturation comes in this magnetic path. Then you know we have iron, and if we have iron, then you have the BH curve, which is well-known curve for the saturation of the iron. This is H, or IF field winding, the field current, and this is proportional to the induced voltage. So if you increase the field current, if you increase the field current here, it becomes linearly, but when you reach to a level of flux, so we have now saturation, and this of course will affect the reluctance of the magnetic path and inductance and so on. So this is the way.
طب دكتور, what about constant resistance?
This is like a non-linear characteristic, or loaded, or you know, this is the loaded machine. Okay, this is the loaded machine. You have load is resistance constant, and you increase the field current. And we have here three curves, like air gap. If we don't have any saturation, if the magnetic path is linear, or iron, reluctance of the iron is 0, يعني permeability equal to infinity, mu r mu او mu عموما mu iron equal to infinity، معناها انه يعني no reluctance for the iron. كل الريلاكتنس جايه من الاير جاب فقط. الاير جاب reluctance تبقى very high compared to the iron of course. So this is the air gap line. This is the we have no load characteristic where we don't have any load. So we may have, this is no load. If you have a load, if you have a load on the machine, then you have such characteristic here. This is let us say constant resistance. This is the air gap. Why do we have here? Then we have now armature current. يعني هنا no load، يعني الارماتشر is open. There is no load. Okay, but when we have here loading in the armature, when we have currents in IA and B and C, this current we have what we call the armature reaction. Armature reaction. So this current will produce flux. So we have now two sources of flux. One comes from the field winding, and the other comes from the armature current. And this armature current will react, will reduce, okay, will be the opposite side, one of the components. We have two components of the armature reaction. One is demagnetizing the component that reduces the net flux. And if you reduce the net flux, then the voltage at the same field current, the voltage will be lower. Am I right? The other component of the armature reaction is to distorting the distorting the field one, the field or the flux in the circuit. So which would be يعني perpendicular to the flux, and this one will be opposite to the flux, اللي هي demagnetizing component. فالفلux بيقل due to the armature reaction, and the voltage will be lower. Okay, is it clear, Abdulaziz?
Yes, thank you.
Okay, so now stabilizing the transformer. What is the purpose of the stabilizing the transformer? Stabilizing the transformer is used for, of course, to improve the response. I should clear this. هنقعد one by one كده. طيب, okay, so this is the circuit of the stabilizing transformer. You have it here like transformer that you can see. You have primary and secondary, and you have here very high impedance here in the secondary. So the current here is almost 0. in the secondary circuit. And we have mutual inductance, we have leakage inductance and the resistance for the secondary, and also for R1 and L2 for the primary resistance and leakage reactance. If you write here KVL and here and here, so you can see the transfer function. Now we derive the transfer function here as, if you still remember from the block diagram, is KF over 1 plus STF. So this is the transfer function of this. So this is the realization of the stabilizing transformer. It can be seen that from the self-excited DC exciter, the KE is negative, and this is why the exciter has a destabilizing effect on the system. So we need to have such a stabilizing transformer. Therefore, the excitation system itself can cause instability. Even without this potential instability, there is a need to shape the regulator response to achieve desirable dynamic response. This can be accomplished by the stabilizing transformer. Let us go here and analyze the circuit where its input is connected to the output exciter, and its output voltage is subtracted from the amplifier input. And this is what we have here in the block diagram. The input of the stabilizing transformer is EFD. This is the input, and this is the output. This is the secondary of the stabilizing transformer, and this is the primary of the stabilizing transformer. Okay, so I2 is approximately equal to 0, and as we mentioned, the impedance here is very high impedance, but this is approximately equal to 0. So we can write the KVL as V1 equal to the leakage and the resistance of the SL here, LDI by dt. So R1 plus SL times I1 plus the mutual inductance dm by di2, or the current in the other circuit. So since I2 is approximately 0, so this is equal to 0, so we can approximate the voltage in primary here as R1 L1 times I1. And we can write also the KVL here equal to L2 R2 plus SL2 times I2, which is almost 0, but this is done, plus M di by dt, so SM I1, okay, plus almost the current in the mid. So you have V2 here equal to SM I1. That's all. I2 equal to approximately 0. So V2 equal to SMI1 plus this one, which is, very small value, I2, so you can write this. So the transfer function, which is V2 over V1, you can write it as SMI1 over this. And of course, you can put it in the standard form as SKF over 1 plus STF. So this is the stabilizing transformer transfer function. Okay, so LKF equal to M over R1 and the TF equal to L1 over R. Of course, you can easily handle this. Any question? What we will consider here in our study is to approximate the excitation system to what we have here in the block diagram. And we eliminate the saturation, we eliminate the stabilizing transformer, the exciter, we assume it. So we have only the automatic voltage regulator. Automatic voltage regulator, gain and the time constant. You have VT here in negative, V reference, and this is the other signals comes from the stabilizer. Later we will discuss this point. We have here power system stabilizer, and this is EFD. If this is the simplified model, so what would be the order of this exciter now? Excitation system. What is the order of this? If we need to model it.
It's first order.
It's first order. We have only one integrator here. So it is first order. So we can write directly if D equal to summation of all multiplied by K, and the if D will be multiplied by this. So we can derive the simple equation as such. So if D dot equal to 1 over TA times KA V reference minus VT plus UBSS minus EFD. If there is no BSS, this is equal to 0. If no controller. So if you have a controller, you have this signal. So this is the EFD dot. So now we approximate the excitation system to the first order model, and you add this to the third order model of synchronous machine, synchronous generator, plus first order of exciter. So the complete model that we have now could be fourth order model. If you consider the third order model here and the first order model here, so you can have the fourth order model of the machine and exciter. Okay. So this is some of the practical models of exciters. In real life, you can have different types of exciter model, and of course, this will reflect the complexity of the excitation system in real life. It is not as this funny shape that we have here, or funny model. This is very simple, just for study. But of course, in real life, we have much difficult with so many limitations, so many non-linearities, BI controller, and this is the automatic voltage regulator. We have some, here, low voltage gates. If it is low voltage, if it is high voltage, you can compare. You have a lot of complexity, as you can see here. Terminal voltage, terminal current, EFD, and so many measurements. But at the end, you have the excitation voltage here. So this type, if you are familiar with the types in real life, you can have it as such. Another model, which is, as you can see here, again, a lot of, this is what we have in, this is the exciter. This is the exciter. The KE comes here. It is 1 over KE plus ST. But the KE comes here in addition to the saturation. And this is the automatic voltage regulator, KA and the TA. And this is the stabilizing transformer, SKF1 plus STF. And you have here, this is the filter or the measuring device. And you have here what we call the, this block is very important. This is called transient gain reduction. Transient gain reduction block. If you still remember, when we discussed the automatic voltage regulator, the KA ranges between what? If you still remember. KA
25 to 30. 50.
25 to 50. Okay. $25 to $50. I mentioned that at this point we can have KA equal to 400, right? But this will destabilize the system. Now we have here two conflicting objectives. We don't need the KA to be higher, but we need also to improve or to speed up any deviation in the terminal voltage. So this block will solve this dilemma. This is the transient gain reduction block. You can have here the KA is very high, but when we have transient, this block will reduce the KA. Usually TC equal to TC over TB equal to 1 over 10. We select in this block TC equal to 1, TB equal to 10. So if we have transient at a steady state, at steady state, what is the impact of this block?
No impact.
Why?
Because the voltage is stable.
الفولتج is stable, and usually when we say steady state معناها ان S equal to 0. There is no frequency, no oscillation. S equal to 0. This is at steady state. So at steady state, this is S equal to 0, so the gain here is 1. So this block will not have any impact on the system at steady state. But when we have transient معناها انه S is high. We have high frequency. If S is high, so this one can be eliminated. And this is equal to 10, 20, or whatever. So in this case, you can neglect this one. So, and this S will go with this S. Okay, so we have TC over TB. So the effect of this at transient period, the effect of this block can be approximated to TC over TB. If you select TC over TB equal to 1 over 10, but this 1 over 10 will be multiplied by KA here. So you reduce this KA from 400 to 10 to 40. So this is called the transient gain reduction block. This is very important also in improving the stability. Any question? Another type of the excitation. Again, you have here, do you have a question? Abaziz, do you have a question?
Yes, Doctor, just to confirm my understanding.
Yeah.
So TGR maybe is used, for example, if you have an increase in the load or you have a sudden voltage drop, this system will regulate the increase in the voltage. Should be gradual and not in an instant.
لا ده we are talking about stability of the system, not the voltage, regulation. Okay, this is the voltage regulation. Voltage regulation comes here. Okay, this is the voltage regulation. This block, the impact of this block will appear when we have a disturbance in the system, when we have a fault. For example, when we have a fault, three-phase fault or whatever the type of the fault. sudden change in the load, sudden change in the system configuration. So you have a disturbance in the system. When you have a disturbance in the system, so we have some oscillation in the system. So this block will provide you with a gain of 1/10. So you have here a gain of 1/10. So this 1/10 will be multiplied by the gain here, which is very high to improve the voltage regulation. So during the transient, during the disturbance, this block will provide you with 1/10. So it will reduce this gain. Okay.
If it is not there, Doctor, what's the impact?
This
On
400,
EFD.
this 400 will make the system unstable. So if we don't have this, so we have to limit ourselves with 25 to 50. And of course, you can go deeper and you can analyze this. You can, by root locus, you can see how the poles of the system will go with the gain here. Okay, so 25 to 50, the system is stable. If you increase more than this, then the system will be unstable. Okay, so to solve this problem, now we need the Ka to be very high. We need to regulate the voltage here. The voltage comes here from the this is the stabilizer voltage. If we have power system stabilizer, and this is the terminal voltage. So we need to regulate the VT and V reference, VT equal to V reference as fast as possible, right? So we need to increase the Ka, but if we increase the Ka, the system will be unstable. If we have a disturbance, the system becomes unstable. In order to solve this, we can say we will keep Ka at 400, but we will add this transient gain reduction block. When we have a disturbance, this block will reduce the Ka by 10. You divide it by 10. In a steady state, this one will not play any role in a steady state. Is it clear, Abdulaziz?
So, Doctor, it's like a constant loop, right? Again, we'll have V reference, which is updated. We'll compare it with V terminal. I'm sorry, the V terminal updated, then we compare it to the reference. And for example, in case of voltage regulation, increase or decrease again, or is it a one-time operation?
لا يعني هو يعني انت you are running يعني plant is operating when we have any disturbance in terminal أو يعني if you want for example to increase the terminal voltage, if you apply here a step input, the voltage was adjusted to 1.01 per unit at the generator. I want to raise it so I have overloading and voltage drop somewhere or some weak areas in the system. So I want to adjust it to 1.05. Okay, so this is V reference. So I would like to VT to follow the reference voltage. Is it clear?
Yes, thank you, Doctor.
So if you apply this, or حتى even on the other way around, يعني if you keep the V reference constant, but due to overloading or so, the voltage will be lower, and then you need to increase the excitation to have more voltage or induce the voltage in the generator. So in either way, you have an error here, and you need this error when comes. طبعا this is if you have the stabilizer, but assume that there is no stabilizer here. So for this error, you need to minimize it. You need to reduce it to 0. Okay. So in order to reduce this error to zero quickly, you need the Ka to be very high. You need the Ka to be 400 or 500. But if you set the Ka 500 and you have a three-phase fault in the system or any other disturbance, the system will be unstable. So let us introduce this block to reduce this Ka during the transient. When we have transient, this one can be approximated or can be eliminated. This is very high. So this block will produce a gain of 1 over 10. So this 1 over 10 will be multiplied by Ka. So during the transient, the automatic voltage regulator will have a gain of 40, not 400. At steady state, it has 400. Is it clear, Abdulaziz?
Yes, doctor.
When I say destabilize the system, destabilize from the angular or angle stability point of view. It's not voltage stability. From the angle stability point of view. And this is another practical, and this is also another type of the stabilizer. If you have of exciter, you have here stabilizer signal terminal voltage V reference, and you end up with EFD here. So this is the exciter, SE and the KE can be added here, and this is some of the measurements and limitations and armature reaction and a lot of complicated stuff here. So this is the automatic regulator, stabilizing the signal, stabilizing transformer, exciter. This is typically the same as we have before. You have here two blocks and so on. I mean, this is another one. You have here stabilizing transformer, regulator, and exciter. So these are some of the typical real-life excitation system. Do you have any question? Any question? So, okay, Ayub Khalifa.
One question, Doctor. VR maximum and VR minimum, this will not prevent the Ka to become beyond the limit?
Of course, someone, if you have a limiter here, so you limit the voltage the signal comes from here.
So this will not affect the TGR operation, or it's not related to each other?
No, it is not. It is not affecting it. And here, you are talking about the signal here. Okay. This is we have a limiter here. If you have, this doesn't play any role in the steady state. Is it clear?
Yes.
If we have transient, if we have any disturbance in the system, this gain will be less. So you are not hitting the voltage here will be less, and the gain here is less now by 10. So you are not affecting the VR max or VR minimum, and you reduce the voltage output here. Am I right?
So in steady state, the VR maximum and minimum, it will control the Ka, and in the transient state, the TGR will control the Ka. It's like this?
No, usually this VR max and VR minimum is set. This is VR max. If you have any any sudden change which is not genuine, any مثلا measurement, noise, anything which is not, فانت you limit the voltage here. يعني instead of having like an overshoot or like this what we call it voltage is here, and then you go up this فانت you limit it, you put it here just to keep or to be in the safe side, or to keep your equipment in the safe side, to limit the voltage output. So this is similar to if you have, for example, op-amp مثلا, op-amp, you have the limit of the plus minus 15 voltage. So any voltage point, whatever below this, if you have the voltage exceed this value, it is output of 15 volt. So this is just for safety of the equipment here. Okay.
Okay.
يعني انت also you may have also here like EFD max and EFD minimum. So this is the excitation system, and this is excitation system. Definitely, you can say this winding needs maximum of the voltage here cannot go beyond مثلا 300 volt مثلا. So this is the limit. Is it clear? So you're not allowing this voltage to be more than 300, otherwise you may have damage here. Is it clear, Ayub?
Yes, Doctor, please.
Another question, Hussein?
Yes, Doctor. Now in this flow diagram, the operation which just before the EFD is by, what is the purpose of by? What is the type of operation?
This is by refers to what? By I didn't remember. By refers to what here? Is it? I can check, and actually I can check. I didn't remember. By refers to what here? You have here the voltage of the exciter, and you have here the excitation. Also, voltage comes from here. So these voltages will merge together here. But what type of function of this by? I can check and see, inshallah.
Okay, thank you.
I will check it. Okay. So any other question? Okay, so let us close this. So at the end of this, Shabab, we have third order model of the machine and first order of the exciter. So now our model now is a fourth order model. Fourth order, 3 for the machine and 1 from the exciter. So our states now is omega dot, delta dot, EQ prime dot, and EFD dot. So these are the states of the model that we will continue with it, inshallah. Okay, now let us see the turbine and the governor. Actually, this part is very simple and there is no much. Sorry, there is no much to say here. So we will go over it quickly. So we will see the turbine function, turbine configuration, turbine types, turbine structure, and the turbine transfer function. So in order to, if you want to extend the model, we mentioned and we have 3 for the synchronous generator, 1 equation for the exciter. If you need to also continue with the mechanical part, which is a turbine and the governor, we can add more equations here to describe this. So we will see the turbine transfer function later on. The steam turbine controls how to control the speed of the turbine. A different situation. Turbine function, of course, it is providing the mechanical steam turbine converts stored energy and high pressure and high temperature steam into rotating energy, which is in turn converted to electrical energy. So it is the thermal energy to mechanical energy and then to electrical energy. So it provides us with the mechanical energy. The heat source comes from the boiler, could be a nuclear reactor or furnace fired by fossil fuel, coal, oil, gas, and so on. Configurations, we have two configurations. We have typical configuration of the turbine, different sections, high pressure section, low pressure section, intermediate pressure section. Low pressure section could be can be divided to 2 sections and so on. So steam turbine with a variety of configuration has been built depending on the unit size and the steam conditions. The normally consists of the 2 or more turbine sections, the machine coupled in series. Each section consists of a set of moving blades attached to a rotor and stationary vans. The stationary vans refer to nozzle sections in which the steam is accelerated to high velocity. The kinetic energy of this high velocity steam is converted into shaft torque by the buckets here or the blades. So this is the typical turbine. You have here high pressure section, and you may have, this is the steam comes here, high pressure steam from the boiler comes here. This is the high pressure section. All are mounted on the same shaft, so they are connected in series. So we have some portion of the torque is provided by this one. So we can take the steam output of this and back to the reheat. We can take the steam here and we reheat it. So we can have it to another section of the turbine. And we have the steam again to low pressure sections. And then we have the condenser and then go back to the boiler. This will go back to the boiler. So this is the circulation of the steam. Each section of this turbine provide a portion of the torque. This could, for example, provide 20% of the torque and of mechanical power. and this will provide, for example, 30% of mechanical power, and this each one will provide 25% of the mechanical power. So here is the mechanical power total, which is the combination of the torques of the different sections, and this is a generator. So this is typically the turbine here. We have two types of turbine. We have what we call tandem compound or series compound, similar to what we have discussed now. We have also another type, which is cross compound. In this cross compound, you have here two shafts. These shafts here in tandem compound, we have only one shaft. So we have only one shaft here for the power plant. Sometimes we have two shafts in the mechanical area. So you can have, for example, the low pressure parts of the turbine is mounted on another shaft, and you have another generator here. So you can have this comes to one generator, and the lower pressure can come to the another generator. So you have two generators here. So this is the cross compound. You have them in parallel. They are running in parallel. Tandem means series. Cross means parallel connection. The sections are all in one shaft with a single generator. Cross compound consists of two shafts, each connected to a generator and driven by one or more turbine sections. However, it is designed and operated as a single unit with one set of controls. And the cross compound results in greater capacity. You can increase the capacity of the system, but of course, definitely this will be at the expense of the control. So, but more expensive and seldom used nowadays. So this is the fossil fueled tandem compound is maybe 3600 RPM. Cross compound, you have two shafts. Maybe the two shafts are running at the same speed, or one at 3600 and the other shaft is running at 1800 RPM. So this is one configuration. Steam chest here or chamber, and this is the the input of the steam, and then goes to high pressure turbine, and you take it to generator, and then you condense and back to the boiler. You may have here single. This is no reheat. So this is no reheat. We may have after high pressure turbine section, we can go and reheat the steam and go to the intermediate pressure section, and then you have a crossover or chamber here, and then you go to the low pressure. Of course, reheat means معناها we have delay, so this will affect the dynamics. The crossover also, that means we have a delay here. So the steam will combine here and then will go there. So this can be represented by the first order model, 1/1 plus ST reheat, and this one also 1/1 plus ST crossover. So this also chamber here also means we have a delay. So this also can be represented by first order model. You may have double reheat, even very high pressure section reheat, high pressure section reheat, intermediate pressure section, and then low pressure sections. These are the tandem compound. All are in the same shaft. They are connected in series. For cross compound, you have such configuration. You have here from the boiler, this is the main steam valve, control valve, high pressure section, reheat and reheat steam valve and intercept valve, control valve also. And this is the intermediate pressure. And these are compound on the single shaft, which running here at 3600 RPM, and you have a generator here. And we collect the steam after intermediate pressure section, and then go to the low pressure section, which is mounted on a different shaft, 1800 RPM, and you have here another generator. And you may have 3600 on both sides. So these are two shafts running at 36. You have high pressure and two low pressures here, reheat and then intermediate and crossover. And this crossover we have two sections here, and we have two sections here of low pressure section, and we have two generation. We have non-reheat, we have single reheat, we have double reheat, we have cross compound also single reheat, and we have cross compound single reheat with different shaft arrangements, and we have cross compound with double reheat. I mean, all these types are there. High pressure, intermediate pressure, low pressure steam turbine may be either reheat type or non-reheat. In the reheat type, the steam, go and increase its temperature and the pressure and bring it back to the intermediate pressure section. كله كلام بسيط. Reheating improves طبعا the efficiency of the turbine. Some units have neither an intermediate pressure section nor a reheater, different types as mentioned earlier, in which case the steam passes directly to low pressure. So you have high pressure and low pressure section right away, without reheat, without intermediate pressure section. On the other hand, some units have two reheater section. طبعا الكلام ده مكرر, and it's just a repetition. The steam exhausted from the turbine is expanded and condensed in a condenser before returning to the boiler to repeat the cycle. As shown in figures above, large steam turbines of fossil fuels are equipped with 4 sets of valves: main steam valve, control valve, reheat stop valve, and this is the main stop valve. This is used to, of course, to stop the steam going to the turbine. If you want to shut down this is used for control. You can allow for more steam, low steam, and this needs, for example, a signal from the governor to allow for more power or to reduce the power according to the load. Reheat stop valve, you can stop the steam in the reheat cycle. Intercept valve, this is also a control valve to this. Normally there are at least 2 of each of these valves in parallel. Many turbines actually have 4 or more control valves operating either in parallel or sequentially. The stop valves are primarily emergency trip valves and not normally used for control of the speed and load. And to stop the machine or to stop the turbine. So it is not used for control. What is used in control is the CV, control valve or intercept valve. So the main inlet control governor valves modulate the steam flow through the turbine during the normal operation. Control valves as well as intercept valves are responsive to overspeed following a sudden loss of electrical load. If you have sudden loss of electrical load, according to the swing equation, B mechanical and B electrical, so this is double delta double dot. In this case, you have or omega dot, let us say. So frequency will go if BE is going down. So we have here overspeed. In order to control this overspeed and bring the speed back to the synchronous and the frequency to 60 hertz, you can play with the control valves and intercept valves that comes from the reheat part. Transfer function. Assume that when we have here the steam chest, reheater, crossover. As I mentioned, this represents a delay. So we can express it as, first order model, first order model, first order model. And the torque comes output from the high pressure, plus the torque comes from this one, plus the torque comes from each section here, give you at the end mechanical torque or electrical torque, mechanical torque or mechanical power. Okay, so it is a combination of summation of this plus this plus this. There are 4 sections on one shaft. Let us say for this configuration we have high pressure, intermediate pressure, and the 2 low pressure sections. And this is the there are a steam chest in front of the high pressure reheater and the crossover. Each of these causes a time lag of steam flow. After the steam mechanical energy conversion, the steam is discharged into the boiler again through the condenser. The block diagram of the type P steam for this one, you can have it as such. You have here the chest, and you have here the reheat 1 and reheat 2. If you have reheat 2, if you have only single reheat, so one block is there. And this is the crossover part. This is the output of the high pressure. This is the friction of the total mechanical power. So this could be, as we mentioned, 20%. And this is after the reheat, you have the intermediate pressure section. And this is the contribution of the intermediate pressure section, let us say 30%. And you have the crossover to 2 sections here, A and B, and each one probably will provide 25% of the mechanical power. So the mechanical power equal to the summation of FHB plus FLB IB plus FLBA plus FLBB. Of course, you can model. If this is the B, you can model here. How many for this block diagram? How many states that we can develop here in modeling? How many states?
It's 4 states.
4 states. You have 4 integrators. You have 4 states. And you can write the signal here. You can write the signal here. You can write the signal here, and you can write the signal here, and you can express BM in terms of all these segments. So these 4 states can be added to the original one, which is 4th order model, 3 plus 1. You can add this 4th order model of the turbine to this one also to simulate the mechanical power. If you want to expand the, if you want to include the effect of the governor there. This is some definitions. Reheat, crossover, control valve, intercept valve, FHP, FIB, FLBA, FLBB. In case of severe system fault, the control valve can be used to shut off the steam power completely, and the intercept valve can be used to divert the steam power directly to the steam condenser to rapidly reduce the steam energy input to the mechanical, to the turbine. The fraction of all these are proportional to this and summation of all these fractions is 1, as we mentioned earlier. The steam turbine control, how to control the speed of the turbine. We have different schemes, depends on the range of the speed deviation. Hussein Ali, please, you have a question? Hussein? Well, the time is over. Huh?
My question is related to the cross compound turbine. Is it related to the combined cycle turbine?
Combined cycle could be يعني هي the same function أو يعني same you know approach. But the combined cycle means إنه the output of the steam you can use it again to it is the same function يعني almost the same يعني. Yes, you can look at it as a combined cycle.
Okay, thank you.
So if you have normal speed, you have a small deviation of the speed within plus minus, for example, 5%. So you can have some control through the control valves and so on. You can adjust it. You can adjust the mechanical power by the you know this one. If you have over speed, if the speed becomes like plus minus 15%, and overstep if the speed comes, for example, 20%, not over, since it is over. So let us say this could be plus minus, but this is over speed, and 15% plus and the 20% plus. So in this case, we need to trip. There is no option. Similar to the you know under frequency control, under frequency protection or over frequency protection, you have to isolate the system. Here also, if you have high speed more than 20%, you have to stop the plant and you have to trip the turbine completely. You have to isolate the steam going to the turbine, stop it. In addition, the turbine controls include a number of other functions such as startup, shutdown controls, and so on. So you can see here with the normal speed, the speed control functions are fundamental. I mean, this is, I think, you know, this is easy. You can read it. Nothing, magic behind it. It is just you can assume it as a reading. If you have over speed up to 15%, and if you have up to 20%, then in this case you need to trip the machine, the turbine. Okay, this is the turbine modeling. If you want to study the effect of the governor and turbine, so you add here we have 3 for the synchronous generator, 1 for the exciter. With this configuration, or even if you neglect one of the reheat and so on, you can have, for example, 3 equations of the turbine. So at the end of this modeling, you have BM dot. You can have BM dot, which goes to the swing equation up. So in this case, you can extend your model if you want to study the impact of the mechanical part on the stability. During this course, we will not consider the mechanical part. We will have only like 4th order model of 3 of synchronous generator and 1 of the exciter. and we will see this in next parts, inshallah. If you have any question, please ask. Time is over. I'm sorry for the 5 minutes more, but I would like to close this subject. Any question?